Okay, momentum. Momentum is a weird thing, because momentum is basically what it takes to change the motion of an object. So we of course realize that if we've got maybe a small car and then a big truck, and they're both going at the same speed, maybe 45 miles per hour, we kind of intuitively understand that it's going to take more force to stop the truck than it is to stop the car. It's going to take more to stop the truck. But kind of a weird thing is if we have two cars that are the same size, and one's going at 45 miles per hour, and one's going at 60 miles per hour, it takes more force to stop the faster moving car. That's what momentum is. It tells you, it's not a force, that's deceptive. Momentum tells you how much it takes to change the motion of an object. And that's why momentum's strange, because it's not a force. What is momentum? How is momentum defined? Well, momentum is defined as the product of mass and velocity. And here's the equation. Momentum is given by P. P is momentum, lowercase p. Okay, and P equals mv. Momentum equals mass times velocity. So we can see, since mass is kilograms and velocity is meters per second, momentum is measured in kilogram meters per second. And that's why it's not a force. A Newton is kilogram meters squared per second. So momentum is a different thing. It's not a force. It's not an acceleration. It's just a construct that tells us how to change the movement of an object. So we've got momentum, and it's measured in kilogram meters per second. So let's talk about something else for a second, and we'll come back to momentum in just a moment. We all remember force equals mass times acceleration from Newton's second law. Okay, we know that acceleration, we can rewrite this, and hopefully this doesn't freak anybody out, mass times delta v over delta t. And we know that's just what acceleration is. Say we multiply both sides of this by delta t, so we'd get f delta t equals m delta v. Now, f delta t is a special thing and doesn't have its own variable, just a special idea. This is called the impulse. And the impulse is in the same direction of the force, and we see force and time, that's Newton seconds. So impulse is measured in Newton seconds. Okay. Why do we care about impulse? Well, because look at the right-hand side of the equation. We see m delta v. Well, mass times velocity, what does that sound like? Well, that sounds like if we had change in momentum equals mass times the change in velocity. Let me see how that's the same. So what we can actually say is, in addition to our fundamental momentum formula that we talked about earlier, momentum is also equal to, or the change in momentum is equal to the force times the change in time, or times the time interval. So two formulas for momentum. There you go. Now the important thing about this second one is, if we know the change in impulse so that the amount of force and the amount of time that force is applied, then we can figure out the change in momentum, and then if we know mass or velocity, we can find, you see how these all can kind of interlock together. So we can find lots of different stuff even if we just know a couple of things. That's the point of these two equations. Okay, I'm going to do a couple quick examples. Examples I'm doing are from page 177 and 178, if you want to follow along there. First one says a base ball of mass 0.14 kilograms. So we know mass is 0.14 kilograms. So 1. Okay. Is moving at 35 meters per second. So we know velocity. I guess it's an initial velocity. 35 meters per second. It wants the momentum of the baseball. Well, that's easy. Part A. If we know mass and velocity, we just know that P equals mv. So P equals 0.14 times 35. Great. I'm not going to do that arithmetic for you. That's not hard. Okay, so part B. It says find the velocity at which a bowling ball mass 7.26 kilograms. So we got a new mass for part B. Change colors. Our new mass is 7.26 kilograms. And we want the velocity it would need to have the same momentum. So whatever momentum this was, we'll just call it P1. Who cares? So we know that, and we know the mass, which we do, 7.22. Then we can find the velocity, and it's that simple. Okay. Basic level momentum problems aren't hard because this is a simple equation. You just plug in the stuff, and you're good. You just have to remember that P means momentum. Not a big deal there. Okay, so the next example on the next page says that we have a baseball, and it has a mass, put MB for mass of the baseball, of 0.144 kilograms. And it's pitched horizontally at 38 meters per second. So initial velocity is 38 meters per second. Now, why am I writing initial velocity here? That'll become clear in a moment. After it's hit by the bat, it moves horizontally at negative 38 meters per second. It's because we also have a final velocity. Okay, so we got a mass, initial velocity, and final velocity. Those are our knowns. Part A, question A wants to know, it wants to know what impulse did the bat deliver to the ball. Now remember, impulse is F delta t. Well, so let's think about what our formula is. F delta t equals delta p. This is impulse, that's what we're looking for, and it equals the change in momentum. Okay. The change in momentum, we don't know, so we have to figure that out. So let's figure out the change in momentum. Well, we know the change in momentum equals m times the change in velocity. Well, that's easy then, because we know the mass, 0.144, and the change in velocity, well, how much did the velocity change? Well, change in velocity, put this in a box over here. Change in velocity is just Vf. Oh man, what was that? Vf. Oh man, let me erase. It's not legible. Vf minus Vi. So really, Vf is negative 38 minus Vi is 38. So our change in momentum is going to be 0.144 times negative 76. And that'll be our change in momentum. And that will also be our impulse, because they're the same. Change in momentum is the same as impulse. So that would be the solution to this one. And it comes out to be about negative 11 kilogram meters per second. So there's your part A. So let's look at part B. Part B, they want to know if the bat and the ball are in contact for 0.8 milliseconds. 0.80 milliseconds. Then what's the average force on the ball? So for part B, we're looking for force. Well, we're going to use our same equation because F delta T equals delta P. Well, so solving for F, we're going to get delta P divided by delta T. We just had delta P. It was -11. Delta T is this, except that's milliseconds. So we have to convert that to seconds. So that's going to be, what, 0.0008. Oh no. Look, it's the Christmas TARDIS. There we go. 0008, which turns out to be, man, computers is fast today. Turns out to be how much? Where is it? About negative 0.00 0.014 newtons, which isn't a terribly lot of force, but you know, we're just making a baseball turn around and go back the other way. The last thing, I'm not going to work, I'm just going to talk about, is in their book. You can look at it if you need to see it, if you're confused or something. Last part, it just says find the average acceleration of the ball. Well, if we know force, which we do, we just found it in B, and if we know mass, which was given to us, we can find acceleration because force equals mass times acceleration. Not a big deal.